Okay, just keep you posted. Today we'll be working on 7.6 and tomorrow will be 7.7. Essentially, today and tomorrow, as well as Friday, you can think of it as opposite sides of the same coin. Remember when we talked about exponential curves, it can go up like this. Of course. Right? Or it can go down. Okay. Yeah, it can go up, it can go down. That makes sense if I apply this to real life. There are certain things where the values go really big and certain things where the values go really small. Today, we're going to look at examples where it does get really big. And then Friday, we'll look at examples where it gets really small and in real life circumstances. And hopefully you'll be able to connect all the math that we've done so far with examples. The 3 days is going to be talking about all the different kinds of word problems I can give you. Because on Tuesday, I am probably going to format the evaluation for Chapter 7 in the form of a quest. The main reason I want to stick to a quest is because Chapter 8 is going to be a large assignment. It's going to be a package assignment on investment and money, right? And so I have to juggle that. Okay, so essentially for the rest of this week, we are preparing for word problems. I promise. The evaluation on Tuesday will not be long. In fact, you'll have ample amount of time to do it. But I need to see you demonstrate a variety of different questions, the mastery of a variety of different questions where the numbers go up. In other words, it's growing, or down. In other words, decaying. Right? Any questions so far? Well, not. Today, we're going to look at when something is growing, exponential growth. So take a look at the sheet. Let me get set up with my stylus. Solving problems involving exponential growth. In the box, in the middle of the sheet, you will see that I have provided a template equation. It's a general equation. And anytime you read growth, you know you can use this equation. So some of you are like, yes, all I need to know is how to use this formula. It's true. It's true. And all of our examples are going to be learning how to use this formula. But part of me as a math teacher wants you to know why it makes sense to put these numbers where we do. All right. So I'm going to start with that. Starting with, you notice that in any given equation, typically the exponent will be something like time. And doesn't it make sense that we start calculating with time equals 0? Right? Time often would start at 0. Does that make sense, everyone? I need everyone's attention here. Okay? Does it make sense that time begins at 0? That's really important, because every time you draw a graph, you're going to start at when x equals 0. Right? If you remember, what is the value of anything that has an exponent of 0? 1. Anything that has an exponent of 0 is 1. And so what is this value? When x equals 0, the y value is 1. It's always going to be 0, 1. What I'm trying to say is this. Every time I have an exponential graph, I have to start at 1. But does that make sense? Is that fair? Is that useful? For example, let me give you an example. I invested my money and I started my investment portfolio with a value of 1,000. Does that start at 1? No, I start at 1,000. Let's make it more complicated. Instead of 1,000, what if I started at 999? How do I change that 1 to 999? Right? So knowing that every single time the every single time the graph will begin at 1, we can use that to our advantage and say, oh, okay, if this value is going to always equal 1, but I want to start at a different number, why not just multiply anything by that 1, anything number we want? So again, it might be falling on deaf ears, so I'm just going to move on. When we have an equation, right? This, I hope you notice that this being my power, this is essentially the same thing. Okay? We have our power, something inside the bracket is our base, and something is our exponent. In this case, is usually going to be time. And just like before, what if I have a base of, let's say, 1.5, and my exponent is a 0? Well, the answer would be 1. What if I have 1.5 to the power of 0? But that was multiplied by 500. Well, it would be 1 times 500. My final answer would be 500. In other words, I start at 500. Using that as our argument, you will see that, we'll use a different color. Whatever number is multiplying to the exponent is going to be my initial value. I'll say it one more time. Any number that is multiplying to the power portion of my term is my initial value. Right? Right now, I have a 1 multiplying to it, so my starting value is 1. Here, I have a 500 multiplying to it, so my starting value is 500. If I want $20, I don't know, you put a 20 there, that's going to be my initial value. I've already mentioned here, my exponent is going to be my time factor. It's usually in years, but I could always change to months, days, even minutes if I wanted to. And you'll see when it comes to the context of the question. Lastly, when we talk about growth, and this is the most crucial part, when we talk about growth, our exponent, so the base, is usually going to be talked about in terms of percents. You need to make sure it's not a percent, but write it as a decimal. So I'll demonstrate it in the next example. Ready? So this might be gibberish to you. I want you to consider this equation. I'll write it out every single time when we do a question. Let's get it done. Here we go. The variables can change letters and to better represent the context. So in this case, you will see me using VF and R and T and blah, 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 but you can always change it into different letters that make sense to you. Here's my question to you. Let's explore. And this is my little segue into money stuff. As a class, I need your participation. How much do you think you need if you want to retire at 65? Let's get some hands up. In this day and age, with inflation and everything, with your limited knowledge of the world right now, or maybe more knowledge of the world than I do in terms of business and finances, how much do you think you'd need if you want to retire comfortably? Think about maybe the conversation you might have had with your parents. Think about your own knowledge of money and how much you might spend. Literally, think about this past month. This is almost the end of the month. How much did you spend with your friends, your food, blah, 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 your cell phone bills if you've taken that onto yourself, right? How much do you think you might need to stop making money at 65? How much money do you think you'd have to save up? Think about it. I really want this to be real to you, so like think about it. Shall we do some math? Shall we do some calculations? All right, everyone. It seems like people are really, really lost as to even how to consider that. All right, let's talk about, and this is something you're going to probably be doing for me for chapter 8, so I don't mind doing this. Let's talk about home. I don't know if you will rent or if you will own, whether you still have a mortgage or not, but how much do you think you'd be spending on your house a month? You know what? Let's create a fictitious thing, okay? Let's say you're renting because you're traveling all over the place. You're never staying in one spot. You're not the type to put down your roots. You want to see the world. You're 65. You're rich. You want to do whatever you want to do. How much are you paying for rent a month? Yes. What? Okay, 1,200. Nice. Sure. So that's times. Sure. Let's do per month. Per month. Okay. Good. Let's talk about selling. How much do you pay a month? Because you'd be like, you know, talking to your friends, be like, hey, I did this, I did that. Are you gonna go somewhere? You want to meet up? Blah blah blah. How much? How much do you pay right now? How much do you pay right now? Say. No. Well, okay. If your parents are taking over right now, sooner or later you're gonna have to take over yourself, right? Your parents are gonna be like, you're old now. You're well, you know, you have the ability to make money if you want to. It's about time you start, you know, taking responsibility for your own bills. I don't know. Those are bills. Zach, do you know? Okay. Oh, all right. All right, everyone. I'll be generous and give you my grandfather plan. I got a plan with Freedom Mobile when they first came out as Win. And so I have a grandfather plan that does not exist anymore. I have a fully, I guess, full inclusive, all over Canada, plus 5 gigs of data, $30. Pretty amazing. Okay, nowadays you can get something like that for like $50. Anyways, let's be 30 a month. Okay, how about food? I'll just leave it at that. Food and entertainment, because right now that's all that's important to you probably. How much do you spend on food? Think about breakfast, lunch, and dinner. Groceries, going out. Oh gosh. Okay, how about a week? How much would you spend a week going out and eating with friends? That's right. Okay. With inflation, 100 would be like going out twice a week. All right, now that you're retired, okay, so 100 a week times, let's say 4, so 400 a month just on going out. Groceries, I'll give you mine. Let's say just to feed my family of 4 now, with inflation, I'm gonna be generous and say we'll spend like over $1,000 a month. Okay, so 1,400. What about entertainment? You're not gonna stay at home and twiddle your thumbs all day. You gotta go out, right? You gotta do something with your friends. You're 65, like you work hard. You gotta relax. Let's say you go to the movie once. Let's say you're the type to pick up golfing like once a week. I don't know. You go to like a book club. I don't know. What do you do for fun? I need a number. I'm wasting time here. 200? I don't know. Okay, let's just say. This is like the most ridiculous thing. You'll see actually how much it costs when we get to chapter 8. 1,200, 1,400, 26, 28, 30 per month. That's still a lot per year. Let's calculate that. 2830 times 12, that gets you 33960 a year. How long do you think you'll live? Think about your grandparents. You know, if you've lost them. I lost mine a couple of years ago. My last grandma, it's a little sad. She was just pushed over 90. So from 65 to how long do you think we'll live? 20 years? 20 years, okay, times 20 would be, sorry, I should be proper. 33960 per year times 20 years Okay, 679,200. Is that fair? That's nothing. Honestly, as an adult, in my opinion, that is nothing to live for 20 years. That is way too low. You need to save up a lot more, or have some other means of income when you're older. But let's be generous and just say it's 700,000, just to be nice. Okay. All right. Going back to our sheet. This is a terrible estimate, but for our purposes, take a look at how I'm writing this. The amount that you think you will need to have at the age of 65. The final value, VF, is going to be 700. Let's write that down. Okay. So I'm going to spin it on you and say, you actually don't need to make all that money all through salary. You can use something called investment. Anyone know anything about investments? A little bit. Charlie, do you know if you put money in the bank, do you know how much the bank is willing to give you if you just keep your money in their bank account? Yeah. Do you know how much? What percent? No. Anyone know what is considered a good investment? How much percent you should be earning every year to be a good investment? Correct. But what percentage?
2 or 8%.
Sort of. A good investment is if you're getting back about a little over 7%. That's like a great investment. Why? They say that the goal is if you can double your money every 10 years or something like that. Anyways, let's say you found an amazing investment opportunity and you're getting back 10%. That equals 0.10 if we're using it in a mathematical equation. You can't put a percent in there, you have to turn it into a decimal. So put a little highlight there. Okay. You need to turn it into a decimal. The number of years you have before retirement. Let's talk about now. If you're 18 years old this year, no. Are you 18 this year or 17 this year? 18 this year? 17 this year. 17 and you're retiring by 65. How much time do you have? Is that for me? 65 minus 17. 48 years. Seems like forever. That's like 3 times how much you've lived so far. And maybe, yeah. Okay, let's calculate how much you need right now. So follow with me. The formula is the final value. I like to write the letter amount, but that's okay. Final value is equal to, or sometimes I call, instead of VF, I call it future value. They're all the same. The final value is going to be the initial value times 1 plus r to the power of time. Shameless plug into chapter 8. If you want to have less of a headache, I could write future value is equal to the principal or the present amount, 1 plus r over t. You can do the same. It's the same. You'll see the textbook interchange it. So let's do this. What's my VF? 700,000. What's my VI? I don't know. Oh, in case you're wondering where I'm getting all this, let me write it there. VF is 700,000. R, we just wrote above, is 0.10. Time, we just wrote, is 48. VI, I do not know. So I'm going to take all this and plug it in. Okay, so very quick, 1 plus 0.1. Mental math, anyone? Anyone? 1 plus 0.1. Yes, thank you. If you have your calculator out, Miss Kaylee, you got your calculator out? Could you do this one? 1.1 to the power of 48. It's either y to the power of x or little hat. Depending on your calculator brand, you'll have one or the other. .017. Okay. So here's a moment of truth. Would you take this equation, divide both sides by 97.017? Because I want VI all over. And tell me what that number is. Whenever someone is ready, I'll take their number. I'm doing this because I hope that it blows your mind. Yep. 72,000. Okay, 7,215.23. Okay, please look at that number. 7 grand. Okay, that's like 5 iPhones. I need you to understand this. That's legitimately like 5, 6 iPhones. Would you agree? Right? That is all you need right now. And you sit it in a investment account for 48 years. And you'll have 6 figures. Almost $1 million. Why does that make sense? I need everyone to, I won't say you need to get excited, but I need you to see the power of exponents. Consider this. Remember the graph? Remember the graph? It does this. So in the beginning, when x is 1, 2, 3, 4, 5, 6, 7, 8, blah, 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 right? It's not very high. But at 48, it's here. So basically what I asked you to do is go in reverse. If I have $700,000 at 48, how much was it when it was 0? It was 7K. That's the power of exponents. It grows really fast, really quick. And we can model this based on our equation up here, A times B of X. It's math. It's just we're putting in the numbers that make sense to our lives. Let's try it one more time. And again, this time it's not going to be money, this next example, but I want you to consider how it can just explode if you give it enough time. Here's the next one. Here's a fun one. I actually put this on a test a long time ago. An alien virus, okay, so sort of like, think of it as COVID, but turns into an alien. An alien virus escapes from Area 51 in Nevada and infects a tourist in Las Vegas, turning them into those slower Hollywood zombies. With me so far? Can you picture it in your head? You've got one zombie, okay? The zombie is slow, but because there are always lots of tourists in the Vegas Strip, victims are easy to find. The number of zombies increase at a rate of 11%. Identify key information to use for your equation and then find the equation. So here's my equation. What are my key features? What do you know based on this? Do we have the final value? In this case, the final number of zombies. Do we have it? Consider the question. No, we do not. So I'll leave it blank. Do we have the initial value of zombies? The starting value for the zombies. How many zombies do we start with? Read the question. Just picture it like a movie in your head. How many zombies do we start with? Absolutely. This time it's a 1. It's not 7,000. It's not whatever. It's 1. How much am I growing by? What's my growth rate? Yeah. 11%, but I can't use percents in this equation. So 11% equals what as a decimal? 0. Yeah, 1. Okay, so this is 11%. And if you're not quite sure, remember 11% is the same as 11 per 100, 11%, because in French, cent is 100, right? Think about it that way. So if you do this in the calculator, you will get 0.11. All right. Time. Do we have time? No. But I know that it's in minutes. So here it is. Putting this together, I have final value is equal to 1 times 1 plus 0.11 to the power of t. And doesn't that look familiar? If you're doing it right, it should look very familiar. It's a function. It's y based on x. It's just that instead of y, we're calling it final value. Instead of x, we're calling it time. That's right. All right, so we've got our equation, okay? Let me put this side by side so that you can see as a comparison. Part B, what's the number of zombies, AKA, what is the final value exactly 2 hours after? So because I have my equation, now this question is giving me the final piece of information that I need. The amount of time is 2 hours, but I have a problem. Look carefully, please. What's my problem with the 2 hours? I can't just plug in 2 hours. Yes? Yes. The question said it was per minute. So it's going to be in minutes. Let's plug it in. Final value is equal to 1 zombie plus, or 1 zombie times 1.11 times 120. All right, people, don't be scared. Don't be surprised. The exponent is 120. Before you put that in the calculator, what do you expect to happen? Remember, based on the graph, my starting value was a 1. So my starting value should be a 1 when x equals 0. But I am now looking at the point 120. Assuming that this is an exponential curve, what do you expect the number to be? Is it going to be at 50? It's going to be at 120? a linear. Take a guess. My base is only 1.11, but I know it's going to be exponential. And my x value is now 120. Okay? Have a mental number in your head and plug into the calculator. Take a guess. Just be like, oh, Mr. Kim is saying it's going to be big, so I'm going to assume that it's way big and call it 1 million. I don't know. Okay? Plug it in. Go for it. 1.11 to the power of 120. You got it? Nope. Go ahead.
74,685.
You see why zombie movies, it makes sense that suddenly the entire city becomes zombies? 11% isn't too big if you look at it as a number, but you let it multiply 120 times. It's huge. A single zombie became 250,000 in 2 hours. And that's a slow moving zombie, right? Guys, I need you to understand the power of exponents. This is why it's so important to understand, especially when we talk about money. And here's a T question, you got to really think about it. So if you haven't been following, I need you to think about this. After 2 hours, the tourists catch on and quickly hide anywhere they can. From this point on, the spread of the zombie slows down to 2% per hour. How many zombies roam the streets after another 22 hours? So let's do this question slowly. Oops. Okay. All right. What's my final value? Well, that's what they're asking. How many zombies are left? So what's my initial value for this scenario? How many zombies am I starting with after 2 hours? How many zombies do I have now? Yeah. Yeah. Okay, that's how much that zombies are now. But what's my new rate of growth? And what's my time? So 0.02, and how much time has passed? 22 hours. And I can use 22 hours because the rate is per hour. So this is 22. Let's plug it in. VF is equal to 274,635, 1 plus 0.02 to the power of 22. So significantly smaller growth rate, okay? It happens, but it happens for another 22 hours. Let's say before the United States comes in and starts like killing them off with their armies, whatever. Yes?
Isn't it the power of 20? That's already after 2 hours?
Oh no, it's an after another 22 hours.
Oh.
So we've already gotten to a point where 2 hours has passed.
Okay.
So in other words, another 22. So how many zombies are now present after 1 day? Then when you're ready, plug it in. Let me know. I have a number. I want to make sure it's the correct one with yours. Hey, there's also a, oh, don't take that one. Yeah, yeah. There's also an exponent law thing you have to do for me. You need to do for me tomorrow class. Yeah. It'll be very quick. What's your number? Anyone? Yeah. So even if my growth rate is 2%, after a full day, we've essentially almost, not quite. To double it, we have to be 5 something, right? But we're getting there. Even at a 2% growth rate, you gave it enough time. So it's growing. Which brings me to not a zombie virus, but our day to day. It's not a zombie virus, but it's still a virus. COVID spreads just as fast if we let it go uncontrollably. And so there's a lot of people who are like, oh, let's not mask ourselves. That's fine to have an opinion, but you can't disrespect the numbers. Whether you get sick or to the point where you're hospitalized or you're asymptomatic like I am in this case, you can't fake the data and you can't disrespect the power of exponents. So if you let it spread, sooner or later, it will spread like wildfire, literally, to the entire population. And even if a slow percentage of, let's say, 1% gets hospitalized, that's still what, 4,000 people. That's worse. Let's say 10% gets hospitalized, because our mortality rate for COVID when it was really high was about 10%. 10% of 400,000 people is 40,000. 40,000 people would have passed away from COVID. It can be scary. And so a lot of people will be like, no, this is stupid. But if we didn't try to mask up and do lockdown, then it would have spread like crazy. So in that respect, you gotta appreciate the math for people who knew, people up there who were calculating this, the people in Atlanta who were in the the virus control center and whatnot. Okay, you gotta respect the fact that they know their math. Yes, Charlie. Pardon me? I did. I'm assuming I did it. So 274,635 is 1.02 to the power of 22. So I would do 1.02 to the power of 22. And then whatever the answer is, I would multiply it with 274,000. Okay. I only have like another 10, 15 with you. We spent a little too much time trying to find a number for our retirement. This is the last bit. Okay, someone hold that number for me. If the population of Nevada was 2.8 million people, how many people survived the first 24 hours? Well, 2,800,000 minus, what was it, 4,000 to 424,000? 580 minus 424,580, 2,000,000. That's how many people still are alive. So with that said, there's a handful of other questions you can do for homework. If I were to give you a question related to growth on your quest next week, would you be okay? I hope so, because right now at this point, I hope you don't fret. These questions are simply matching questions, right? So if I have a bunch of questions down here where you can sort of mix and match and create an equation on your own, I hope you can do that. I want to give you one last style of questions. It's when you get a graph like this, right? So here is a graph that tells you how much time has passed on the bottom, how many bacteria cells are on the y-axis, okay? The size of a yeast culture is measured each hour, and the results are displayed on the graph shown. From the graph, estimate the initial number of yeast cells. How many cells did I start with? It should be immediate. How many cells did I start with? Go. Where am I looking at? Yes, thank you. You're looking right here. When time is 0 is what I would start with. So I would have had 20 cells to begin. Estimate the number of cells after 30 hours. So looking at the graph, 30 hours is right there. So I'm going to climb this graph. It is a Y value right there. So what value is it? 80. After 30 hours, so just over a day, it has quadrupled. It's 80 cells. Part C. Use the initial amount to estimate the length of time required for the number of cells to double. What does that mean? How much time does it take for the number of cells to double? Charlie? How did you get that? Good. 20 is what I started with. So just doing some mental math, 40 is my doubling. So if I have doubled, how much time would have passed? Finding this equation, it looks like it's going to be about 15 hours for it to double. Use an amount other than the initial amount to determine the length of time required for the number of cells present at that time to double. Determine the length of time required for numbers. Oh, okay. So use another situation. So I'm going to choose a random number for you. I'm going to do 30. It seems that 30 is approximately at, you know what? Forget the 30. Why not just use the 40? You already established that 40 was at 15 hours. If I want to go from 40 to 80, in other words, if I want to double, how much time did it take? Look at the graph. Yep. Another 15. Oh, is that a coincidence? Maybe. Okay. It took another 15 hours to double. Describe what you noticed about the two doubling times. Check what you found with a different amount on the graph. Well, to go from 20 to 40, it took 15 hours. To go from 40 to 80, it took another 15 hours. Coincidence? Not really. But either way, there are questions like this that ask you to analyze the graph by looking at it very carefully. That's the end of today's lesson. In preparation for our quest, I am going to be giving you examples like this, where you need to be able to identify as many of these as you can so that you can create an equation. And then using that equation, solve for answers that I ask for. Yes, Charlie. Because 40 is at the 15-hour mark, right? How much time did it pass for it to reach 80? Well, 15 hours, add another 15 hours, it became 30 hours, right? So the amount of time that passed is 15 for it to double. Okay. That's it. I'm not going to do number 3 because the bell is going to ring very, very soon. But if you would take today, you haven't had homework in a while, right? If you would take today to try to finish number 3, number 4, number 6, number 10, and of course number 11, it would be really good for you. The answer keys are already there. Particularly, if you want to prepare for this quest, I highly recommend questions for number 10 and be able to identify number 4 as well. Number 4, number 1, number 4, number 10 are, I think, the good places to start for your quest. Any questions? Give that a shot. The answers are available on the bottom. We'll stop here.